Hey guys, welcome back to our channel. This is Remy from Do and Learn. So today we are going to learn about digital circuits and Boolean algebra. So moving forward, so let's try to understand what are all the different basic logical operations that we have. So let's get started with the first operation, that's OR, which is represented by A plus B. Okay, and the second operation is AND, which is A dot B, or we can just put it as A product B. And the third one is NOT, which is also called as complement. Okay, so this is a single operand operator, so it works on a single operand, whereas the other operation works on minimum of two operands. And then we have an XOR operation, which is again a logical operation. Okay, A XOR B, and this is a symbol what we use for XOR notation. And then we have XNOR, which is exactly the complement of XOR. Okay, so this can be even written in such a way like A XOR B, the whole complement. That is also possible. Then we have another universal operation we call it as NAND, which is a complement of A and B. Okay, so it is like A and B, the whole complement. So we can write it in this manner also. Then the final logical operation what we have here is NOR, which is a complement of OR operation. So it's A or B, the whole dash or whole complement. So let's try to understand the various truth values of these operations. The first one is OR operation. When we have two input variables A and B, when we have an operation A or B, then the outcome is based on these two inputs. If any one of the input is 1 or high, then definitely the output is also high. As you can see here, either A or B, if both of them are 1, or if any one of them are 1, the output is 1. Whereas only when both elements are 0 or low, the output is also 0. So this is as per OR operation. Moving further, we have an AND operation where only when we have two inputs as 1, you will get an output as 1. If any one of the input is 0, then definitely the output is also 0. It means that when you want to get a high value as an output, both the inputs should also be high. So that's about AND operation. Moving further, we have NOT operation, which is just the complement of the input. So sorry for this. So this will be like 0's complement is 1. There's a small printing mistake. So 1's complement is 0. Okay, so this is A complement. So that is NOT operation. Whatever input you give, that is inverted. Then you have an XOR operation. So according to your XOR operation, if both the inputs are same, then the output is 0. When both the inputs are different, then the output is 1. So as you can see, we have two different inputs. So the output is 1. And here we have same input. So the output is 0. Okay. Then we have an XNOR operation, which is exactly opposite or complement of XOR, like we have seen in the previous slide. So this is written with the help of this kind of notation, a dot followed by a circle. So as you can see, when both the inputs are same, then the output is 1. When both the inputs are different, then the output is 0. So that's what you can see, and it's just the opposite of XOR. Then we have the truth table for NAND. So when you have a NAND operation, it is just the opposite of this AND operation. So it means that when both the inputs are high, the output is low, and all the other operations, the output is high. So if I have 0 in any one of the inputs, the output is always 1. But when I have 1 in both the inputs, the output is 0. That's what we have with NAND operation. Then we have NOR operation, which is exactly the opposite of OR operation. So the opposite of OR operation is 1 followed by 000. So when both the inputs are 0, the output is 1. Otherwise, the output is 0. So that is the NOR operation. So using this, we can just have a view about the structure of the gates, which will help us to implement these operations. So the first one is OR gate. Okay, so this is how it is drawn. The second one is an AND gate, the logic gate, and the third one is a NOT gate. Okay, you have to be careful with the bubble which is present after the triangular shaped diode, okay, because when we have a gate like this, it refers a buffer, okay. Only when we have a small bubble, it refers a NOT gate. So both the gates are different. So you have to be pretty sure about this. Then we have the NAND gate, where you have an AND followed by a bubble. So this is your NAND gate. Then we have an NOR gate, which is an OR gate followed by a bubble. So the output is complement of A or B. Then we have an XOR gate. So XOR gate is similar kind of an OR gate, but we have a curved line before the OR gate. Yeah. So this is XOR. And similarly, if we have a bubble after the XOR gate, that is your XNOR gate. Okay. So these are the gates which are used to represent these logical operations. So with the help of this, we can define what is Boolean algebra. Actually, Boolean algebra is an algebraic structure that has got two operators with it. One operator is plus and second one is dot. And also this algebraic operation deals with only two numbers in this set. So one is 0 and one is 1, because we are dealing with binary numbers. And that's why we have the name called as Boolean algebra, okay. So when we have Boolean, we have only two values, either it is true or false. So true is represented by 1 and false is represented by 0. So with the help of this Boolean algebraic interaction, we can try to understand certain postulates and theorems based on this. So the first postulate is that Boolean algebra is closed with respect to the operator plus and dot. So what do we mean by this? So it means that if we have an operation that is performed with the help of these two operators, okay, with the help of inputs what we have. As I told you, we have two inputs, 0 and 1, and we have two operators, one is OR and second one is AND. So when we operate with the any input with the help of any one of the operator here, the outcome what we obtain will also be one among these inputs. So we can even check with any other operation. So 0 and 0, that gives us 0. That is again present in this set. So when we operate any two operands here with the help of these operators, we cannot get a value that is apart from these two numbers in this set. So if we have such a set, then we call that as a closed set. And Boolean algebra is closed with these two operators. So that's the idea here. Then the second one, for every operation what we have here, we will have an element called as identity element. So what is the property of an identity element? Let's say an identity element is 1 with respect to the operation called as AND. Okay. If 1 is an identity element for AND operation, then it should satisfy the property 1 and any value for x should be equal to x. Sorry, this is AND, so I should just make it as dot. So 1 and x should be equal to x and 1. That also should be equal to x. So let's take any one value for x. So it can be either 0 or 1, and we can test out. So 1 and 0 is equal to 0 and 1 is equal to 0. So 1 and 0 obviously is 0. 0 and 1 is also 0, and that also is equal to 0. So this property is satisfied. So 1 can be considered as an identity element for the operation called as AND. Similarly, there is another identity element for the operation called as OR. Okay. So 0 is the identity element for the operation called as OR. So if you want to check this, what we can do is 0 is the identity element, the operation is OR. We can have any value for x should be equal to x, or 0 should be equal to x. Okay. So let's take a value for x such as 1 or even 0 if you want, but I am considering 1 here. So 0 plus 1 or 1 is equal to 1 or 0, that should be equal to 1. So 0 or 1, you know that it is 1. 1 or 0 is also 1, and that is equal to 1. So this property is also satisfied. So according to your Boolean algebra, we have two identity elements with respect to both the operations. The first identity element is 1 with regards to AND operation, and the second identity element is 0 with regards to OR operation. Now moving further, This Boolean algebra is commutative in nature. So anything like A or B will definitely be equal to B or A. And also we can have like A and B will definitely equal to B and A. These are the just two operations what we have in Boolean algebra. So we cannot go beyond this. So this property is also confirmed. So you can take an example for A and B. Like when I take 1 for A and 0 for B, we can just check whether this is equal to 0 or 1. So 1 or 0 is 1, 0 or 1 is also 1. So the property is satisfied. Now moving further, let me erase this before we move further. Okay. So Boolean algebra is also associative in nature. So what do you mean by this? So A plus B plus C should be equal to A plus B plus C. So this is some basic mathematical associative property. Let's try to check whether this holds right. Let's take a value of 1 for A, a value of 0 for B, and a value of 0 for C. So on your left hand side we have 1 or 0 or 0, and on your right hand side it is 1 or 0 or 0. So this 0 or 0 will give me 0. So 1 or 0 is in my left hand side. This 1 or 0 will give me 1 or 0, that is left out. So 1 or 0 is 1, and here also we have 1 or 0, that is 1. So it's all also okay with associative property. And the next property what we are going to see, or next postulate, is distributive property, which says that when I have a combination like A plus B and C, this can be written as A or B and A or C. And equally you can prove this one also. And another version of distributive property is that when we have A and B or C is equal to A and B or A and C. You can just apply the values for A, B and C, and you can find these values to be true. That we will be seeing in the near future. Now let's go to the next property. So the complement property says that A's complement, the whole complement, will give us A, the natural value. And the final postulate what we can see here is there exist at least two elements X and Y in B such that X naught is equal to Y. So what do they mean by this? So as you know, in our set we have only 0 and 1. Let's take this value as X and let's take this value as Y. So definitely X complement will be equal to Y. That's what they are trying to say. So X complement is 0 complement, that should be equal to 1. We know that 0 complement is 1, so 1 is equal to 1, hence it is proved. Suppose if you interchange this one, let's say this is Y and this is X. Again, then let's check X complement whether it's equal to Y or not. So X complement is 1 complement should be equal to 0. 1 complement is obviously 0. So 0 is equal to 0. Hence this part is also proved. So based on this, we can understand we have around 7 different postulates which describes the basics of Boolean algebra here. So we are at the end of the session. So thank you for your time. If you have any queries, please do email us, or you can write in the comment box so that I can answer your queries. If you like this video, please share and subscribe to our channel. I'll see you in the next video. Thank you.